I mentioned briefly in class how it is often a viable approach to use a table or to use established formulas of integration to solve integrals if we're not really sure what strategy to approach. And since we really covered some of the more basic, not these are particularly easy strategies, there are a lot of more difficult integration strategies that are not in our curriculum, but would be covered in a Calc 2 class or something. But at the end of the day, we can always look at a table and try to interpret the answer from there. So let's just practice solving integrals by using a table, and you can do the same thing with a computer. But let's go ahead and check some of the answers we got before and see if we can confirm our answers that we got via integration by parts. So in class, we did the antiderivative of 3x e to the x dx by using the integration by parts formula. Let's see what we would get if we were to use a table and just kind of cross-check ourselves. So if we wanted to find it, notice that if you look at actually number 6 and 7 have to deal with algebraic, x power functions multiplied by exponential functions. It even has exponents, an a factor within there, just in case you were to have one, which we don't. But looking at 3x e to the x. Also, notice since there's no 3 there, what we could do is pull the 3 out front just to, as I've been doing quite often, just to make it look exactly as we see it in the formula. And this would leave us with number 6, where we have x times e to the ax. And a would just be 1 in this case, because we don't have a number on the x. So this should be relatively easy following through with the formula. Basically, a is 1, otherwise that's it. So we're going to leave the 3 out front. Also, just like I said before, if I'm using a formula to this expansion, I want to make sure that the 3 is multiplied by the whole formula. So 1 over a squared, since a is 1, would just be 1. This would be multiplied by e to the ax, which is just e to the 1x. So I'd have e to the x. And this would be multiplied by ax minus 1. Again, a is 1, so basically what I'd end up with is this. And I'll go ahead and tack c on at the end. Remember, it doesn't really matter where you put that because it is arbitrary. And actually, this looks a little different than the answer we got in class. I know I don't have it here in my on my computer notepad. But if we were to distribute this all out, notice I would have 3 e to the x times x, or, I'd usually write that as 3x e to the x. And then 3 e to the x times 1 is just minus 3 e to the x. And if you go back and look at, your notes from live class, I'm pretty sure that is exactly what we got. Again, it's been, a few hours since we had class, but there we have it. And if we got something else, well, we know we were wrong or we used this formula wrong. So it's a good way to double check ourselves when we don't know for sure. Or say, for example, the antiderivative of ln of x, we did this by integration by parts as well. Notice that, number 8 just has exactly that. Excuse me. And it says the antiderivative of ln x is x ln x minus x plus c. So that one is obviously really easy because it's just there. But again, sometimes you might see a formula and you might have, well, why? Where the heck did they get this formula from? And often it is from various integration strategies like IBP or U sub, or even some of the other ones I mentioned in class, but we're not going to worry about. Or, say we had the antiderivative of an exponential function, or, something like that. We talked about the derivatives fairly extensively right before the first test, but we could go look up the antiderivative of an exponential function base a, and what it says is a to the x divided by the natural log of a. You'll notice that's exactly the opposite of the derivative. So here a is just 4, so I'd have 4 to the x divided by ln 4 plus c. And if you remember, the derivative of an exponential function, a to the x, was a to the x times ln a. So it's not really surprising that the antiderivative, which is typically the opposite of a derivative, gives you division by ln a instead of multiplication. Now let's say I want to do x ln x. This is one I just recorded a couple videos ago, and I don't know what happened to it. Maybe I didn't record this one, but let's say we wanted to know what the antiderivative of x times ln x is. Let's see if we can find it. Looks like number 10 would be that one. Any x, any power function times an ln. And this formula looks a little bit worse, but here n is just 1, so again, fairly easy to apply. Let me scroll out just a little bit so I can look at this while I write. But we would have, so this should be equal to x to the n plus 1, so that would be x squared, because n is 1. And that would be multiplied all by bracket ln x divided by n plus 1, so that would be ln x over 2, minus 1 over n plus 1 squared. So 2 squared is 4, minus 1/4, and all of that should be plus c. And actually, I think we did this one in class because this one looks familiar, but notice if I use the distributive property here, I end up with x squared ln x times 1/2, and then minus x squared over 4 plus c. And yeah, this looks very familiar. I'm pretty sure we did this one in class too. But again, we can check them out by using just a formula sheet. Very nice. And also, if you want to use a computer calculator, of course, this is something that's not allowed to use on an exam, but like some advanced calculators, or even a website like, I don't know if you've ever heard of Wolfram Alpha, but a lot of like online calculators can actually do very, very advanced calculus. But basically, how you can tell it to do an integral is just say integral, and let's say we want to do x times ln of x. And then I'll go ahead and type in dx. I'm not sure exactly, I don't remember exactly how they need you to input your answer in, but that is one way to get it to go. And notice what it will say is, it says integral of x log x is equal to 1/4 x squared to log x minus 1. And this actually looks a little different, but notice that actually what it says in the corner is log x is a natural logarithm. And this is something that's worth noting, that a lot of actually advanced modern calculators treat the common log as base e, not base 10. So almost all mathematical textbooks treat log x as base 10. But we know the natural logarithm is base e, and that should be what we're getting here. So if you're ever confused by that sort of thing, basically this is ln. They just call it log. Instead, it's an annoying difference of notation. But anyways, and there'll be a lot of other stuff on Wolfram Alpha that is difficult to understand because it's getting into more advanced mathematics. But nonetheless, it is consistent. It says 1/4 x squared, which is negative 1/4 x squared is this component, and then we've got x squared, 1/4 x squared times ln x times 2. Well, again, 2 times 1/4 would be 1/2, so that is the same. Now, say we're moving into some of these other examples, like 1 over x squared minus 25. This one could be solved by something that's called partial fraction decomposition, which is an algebraic headache. Well, it's not so bad, but it's something that most algebra students do not learn. But what we would get, if we were to just use a formula, we could go peek for, notice it would be number 14, x squared minus a squared, not 15. There is a slight difference between those two. But number 14, applying the formula, here a squared would be 5, because notice it is a square. But basically, you need to take the square root of this number to get a. So the antiderivative of 1 over x squared minus a squared, it says is equal to 1 over 2a, so that would be 1/10, times the natural log of the absolute value of x minus a over x plus a. And again, a is 5. Absolute value plus c. And the reason this works this way is it has to do with the factorization of the difference of squares, x plus 5 and x minus 5, and basically you can break it down into separate things and blah, blah, blah. But anyways, we get our answer. Cool. Looking at one last example, this one we did a fairly similar example using IBP, but again, we could always consult the table to see if there is an easier formula to approach it with. Notice if we're looking at number 24, it appears to be quite close. We have x times a plus bx. Another thing you might wonder is, well, this is not a plus, not a minus. Does this formula work in this case? And something you should be quite careful about. Let's just go ahead and give it a try. So here, notice that b would be 3 and a would be negative 4 because the term that's on x is b, and they don't write it as mx plus b, which is a little annoying, but that's fairly common with linear functions in some texts. But yeah, so let's go ahead and use formula 24 and see what happens. So we would get, well, it says 2, this one is quite a complicated formula, 2 over 15 times b squared. And again, b is 3. So 2 over 15 times 9, I'm too tired to try to do that math in my head right now, is 135. And that would be multiplied by, it says 3bx. So again, that would be 3 times x, 9x minus 2a. So a is -4, so minus 2 times -4 is plus 8. And then it says it's all of that times a plus bx. That's just the original 3x minus 4 to the 3/2 power plus c. And so it's not so bad after all is said and done. But you could use an almost exactly synonymous procedure to this, though it actually would be a little bit more annoying because you'd have to use u sub on top of integration by parts to solve it by hand. But as we can see, it ends up being a fairly simple result at the end of the day. And anyways, that wraps up this chapter 4. And again, technically, the section on tabular integration is in the appendix instead. But I think it's worth showing you guys and getting some practice in, because these are formulas you could, for sure, put on your note page. Obviously, I would not recommend putting all of these because they're very obscure, very random, and I'm not going to ask you anything that you can't solve via u sub or integration by parts. But you never know when you would need it.